Just to give a little impression of the intention of the talk, I know I have around 30 minutes, so of course it's a little limited what you can actually make happen within those 30 minutes. But I would like to, I have the ambition of illustrating how CP compliance can be made very simple, also under complex interference conditions. So those 8 bullets, I hope to be able to go through them. The first one is just a little recap of criteria for basic cathodic protection and criteria for at least AC interference. What are the standard requirements? I would like to illustrate for you the very basic principles of the ER probe for corrosion rate measurements, and in particular in connection with external pipeline corrosion. I would like to illustrate or maybe recap just a basic understanding of AC corrosion. Also, I would like to illustrate what I call the corrosion rate concept that implies measurement of corrosion rates on top of electrical fingerprints. Illustrate that concept in relation to the standard requirements, how we are going to use them in a simple way. And also bullet number 6, how to mitigate AC currents by DC adjustments and save money. And this is what Amajit so promoted a little bit on how can we do that a little bit easier, or how can we combine at least DC adjustment and grounding system in order to save some money. Also, how does a corrosion rate test station installation look like? And I have some examples of data and their simple interpretation. So first, this illustration is a buried pipeline, as you can see here, with different sort of components. We have an isolating joint. We have maybe interference from AC, high voltage AC power lines. We may have a casing here. We may have a interfering train. And measuring cathodic protection under these circumstances provides different kinds of challenges. So therefore, we do have different kinds of measurements that we can take, that we can make in order to illustrate the effects of these. And what I'm going to focus on today is in comparison with a simple potential test station that simply measures the pipeline pipe to soil potential and maybe also the polarized potential of the pipeline. These simple measurements, they do not really apply when you, for instance, are nearby or parallel with high voltage power lines. And this is where the corrosion rate test station comes into place, and where it can play a very significant role in simplifying how you can assess if your CP and cathodic protection is under control. So about standard requirements, we do know, all of us, that NACE SPO 169 is the NACE or AMP standard on general cathodic protection for buried pipelines. And I would like to focus or draw your attention to section 611, saying that a commonly used benchmark for effective external corrosion control is a reduction of the corrosion rate to 0.025 millimeter per year, that is 1 mil per year, or 25 micrometer per year or less. So actually, we need to recognize that the basis for cathodic protection and applying cathodic protection is simply because we want to reduce the corrosion rate. Section 612 tells us that in selecting the methods or criteria for a specific pipeline, the following are responsibilities of the user: to determine the level of corrosion control that is necessary and sufficient to address the specific condition, to include a means to evaluate the effectiveness of that method or criterion, whether used separately or in combination, to document the effectiveness of CP or other external corrosion control measure, and in the absence of such documentation, at least one of the criteria in section 6.2 shall apply. And 6.2 are the well-known criteria. We have the 100 millivolt cathodic polarization criterion. We have the structure to electrolyte potential of minus 850. That might be the polarized potential or the potential including an IR drop, the current applied potential. And when this has been measured, you must consider the magnitude and the significance of the IR drop. So if you have MIG or risk of MIG, the potential should be minus 950. If you have a uniform high resistivity, well aerated or well drained soils, polarized potentials can be less negative than even minus 850. So I'm taking the opportunity to draw your attention to this because it kind of brings in some a little complexity in when to actually choose one above the other potential criterion. And if you have measuring the on potentials alone, you should do a lot of things in order to justify what is the significance of your IR drop. So what you really usually do is to make sure you have sufficient and enough cathodic protection by dosing the cathodic protection far more negative, maybe than minus 950 millivolts. So if we turn to the AC corrosion standard, that is the NACE SP21424 on AC corrosion. Section 6 will give you the criteria for how to make sure that you have your AC corrosion under control. And 6.1 is based on corrosion rate. Effective control of AC corrosion can be shown by a documented corrosion rate less than 1 mil per year, which is a commonly used benchmark for effective external corrosion control. Then there is criteria based on current densities, saying unless effective AC corrosion control has been otherwise documented the corrosion rate, the AC current density should not exceed a time-weighted average of 30 amps if DC current is higher than 1 amp per square meter, and DC current is the cathodic protection current density, and 100 amps if the DC current is less than 1 amp per square meter. And these current densities are measured on coupons. There is something about AC voltage. The AC voltage induced on a pipeline is the driving force for AC corrosion. The AC voltage should be mitigated to a level where the above current densities are met. One question that always is asked is, well, how low do we need to go in AC voltage? And the simple answer is, just as it tells you in 6.3, you need to be lower than defining these AC current densities. And there's no actual value for AC voltage. Unlike when we're talking about safety, the usual threshold is 15 volts. There is a note on cathodic polarization. AC corrosion is indeed inhibited by cathodic polarization. So the criteria that we just mentioned before in NACE SP0169, they shall be followed, but the cathodic DC current density given here in 6.2 should also be noted. And then there is a tricky one here. Those criteria that I mentioned here shall be documented for a representative period of time, accounting for variations in influencing parameters. So that's really up to the user so far, at least, to define what is a representative period. Let me turn to the ER probe principles, because those standards here, they did justify heavily in my ears at least, that you should be able to document a corrosion rate. And one way of one very common way of documenting a corrosion rate is by using an electrical resistance probe. So just to recap very briefly, an electrical resistance probe consists of a metal element, a steel element, that you embed into a probe. And you do utilize that when you know the dimensions of this metal element, the width, the length, and the thickness, you also need, you have a very well-defined resistance of that element measured from here to here. And that resistance depends exactly on the dimensions. So you can rearrange this equation and you can get the thickness as a function of the resistance of that element. And when the resistance of that element will increase, it's a measure of the decrease of the thickness of the element, and therefore this is an indicator of corrosion. So you can reformulate again to measure the corrosion rate as a slope, a time slope of the resistance curve, and therefore you can derive a corrosion rate from measuring continuously the ER values. Right? The drawback of this principle is that not only the dimension of the element affects the resistance of the element, but also the temperature. And therefore you need to embed another element inside and shield it from the environment so that you have two elements, one reference element and one exposed coupon element. And you constantly compare by sending an excitation current through those different elements, measure the voltage drop. You can compare the how those two resistance values are developing. And since the reference element is not corroding, it depends only on temperature, and therefore you have one mean of a primary temperature compensation. So the next thing you need to worry about is since you have current exchange between the soil and this metal surface, the metal surface of the coupon element, which is not present on the reference element, you do have a local heating of the coupon element, which is not occurring on the reference element. So you do need, in order to make reliable ER measurements that can be used to quantify corrosion, you do need to have a secondary temperature compensation in place as well. And that's what we have in our types of probes, at least. This is how the electrical resistance probes can look like. There is a circular one with a spiral element here, or like this. The one that we sell, at least, is a rod type element in 1 square centimeter for AC corrosion. And you saw from the different equations that we have that we can optimize on the design of that probe in such a way that the time you need in order to have enough resistance change to measure a certain corrosion rate can be optimized, and it can be described very well, for instance, by drawing these lines between what is the actual corrosion rate and what is the response time of the probe. I have one example here. For a corrosion rate of 100 micrometer per year, our probes, our type rod type probe, will give you a response time of about 4 hours. So, and if the corrosion rate is even higher, say 1000 micrometer per year, it's a little bit more than half an hour we can have a response time. So that's the backbone of the corrosion rate concept. And by combining such a probe with electrical fingerprints, you do have what I call the corrosion rate and electrical fingerprint concept. We do combine measurements of the thickness of an ER probe. The ER probe is installed next to the pipe. We do have a connection to the pipe, of course, and a test post in which there is a data logger and also a reference electrode attached. So you can make all the usual measurements that you are measuring. You can use the probe as a coupon, exactly like a coupon that on which you can also measure a corrosion rate. So what you can measure in this type of test station is the thickness of the ER probe and thereby the corrosion rate, the on potential, which is pipe versus ref, IR free potential, off potential of the probe or the coupon, the DC current density that comes to the coupon. You can also measure the pipe to soil AC potential, and you can measure the probe AC current density, and you can measure the spread resistance, which is the ratio between AC current density and AC AC voltage and AC current density. So that gives you the opportunity to compare the corrosion rate that you measure with all the different, what I call electrical fingerprints. And we can measure this throughout time, and we can align all the plots of these different quantities so that we can analyze if you have any kind of corrosion, under which circumstance, I mean, what is the electrical fingerprint that actually gives you that corrosion rate. And on that basis, you are very close to actually diagnosing what is the cause of this corrosion that you're seeing. Remote monitoring can be made, or you can make data logging or spot measurements. These are the instrumentations that we use. We have 3 different kinds of instrumentation. Don't want to get too much into that. The test station concept, this data logger can be fit into different kind of test stations. We have a big Fink traditional test station, could be with a solar option. It could be a junction box. It's easy to operate also with a solar option, or it could be a subterranean bullet that we bury in the terrain so that everything is actually hidden from the public, if that's a problem. So test stations do have a wide variety of appearances, just according to client need and client wishes. A little bit on AC corrosion, since I'd like to illustrate some examples. It requires just a little bit of basic understanding of AC corrosion. And in AC corrosion, Metricorr have been studying AC corrosion for 25 years. It's actually the basis of the whole foundation of Metricorr is AC corrosion. So we have had a 20-year long scientific approach to AC corrosion, and from that we have developed our remote monitoring or monitoring units, that is. So I'd like to take the onset in this equation here, which is a very simple equation that ties together the AC voltage and the AC current density. And it's the usual equation that you're using if you would like to make a model of AC voltage along a pipeline. And then after that, when you have made a voltage profile, you can start guessing on what kind of or what level of AC current will be flowing through a certain coating defect. And therefore you have the anticipation that the soil resistivity will play a role, and also the geometry and size of the coating defect. And I'd like to stress out here that this factor here, this is what I call the spread resistance. This factor is really not only depending on the soil resistivity, because you will learn that if you start making a cathodic polarization by applying some cathodic protection current to a coating defect, at a certain point, if you display that amount of cathodic protection current through and show the spread resistance on the y-axis, you will see at some point you start to have excessive cathodic protection current density, meaning that you take control of this environment. It's no longer the soil resistivity, but the environment that you create with your cathodic protection that define the value of the spread resistance. So if you come beyond a point where you put excess cathodic protection, the only thing that will happen is that the spread resistance will decrease, and it can decrease a whole lot. And therefore, if you do take note of Ohm's law here, you will see that the resulting AC current at the same level of AC voltage will actually start increasing a lot. So you can come into a situation where the operator itself, by not having control of DC, will create a situation with low spread resistance, and this is when AC corrosion starts coming through. It's very simple. You do consider your pipe surface with a coating fault, you are making cathodic protection, meaning you are typically reducing water molecules into alkalinity. Alkaline molecules like OH-, they will carry a charge, and therefore they will be adding to the conductivity of the soil very close to the coating defect. And this is what is causing the decrease in spread resistance here. So eventually, when you have created a whole lot of OH-, you have a very low spread resistance and your AC current is increasing, and you reach a point where you actually reach this very high pH corrosion area, and typically this is what gives you AC corrosion. So just to illustrate the autocatalytic circle of AC corrosion, as prerequisites, you have excessive CP, you have a small coating defect, and you have some induced AC. And when you have increased AC current, this AC current in itself will cause a depolarization of your cathode, meaning that you will create automatically more DC current. You also have the intuitive action that you would like to make a thorough mitigation. You would like to really add cathodic protection in order to mitigate this AC current. So what you're actually doing is you create additionally excessive CP. This excessive CP will turn to reduced spread resistance. By Ohm's law, you will have increased AC current, and then you will start this circuit of autocatalytic AC corrosion that comes through, and you will create your own problem actually. Right? Now again, I'm not. So if you would like to know more about the mechanisms of AC corrosion, this was just a little glimpse. I invite you to go to the Metricorr website, and you can download for free a PhD thesis on AC corrosion on cathodically protected pipelines. These are for those of you who are scientifically interested in this subject. So let's turn to test station measurements. What can we measure? How can we utilize the corrosion rate concept? Let's compare with a usual polarized potential concept, where in this case you are measuring throughout time the DC potential of your pipeline, and in this case you're measuring in the unconditioned -1.6 and somewhat less polarized in the IR-free condition. You would say that in this area you're safe, and here when you depolarize or lose the cathodic protection, you would say I'm not that safe. So if you measure the ER probe measurement or the corrosion rate concept, your eyes would be on the thickness of the ER probe, and as long as the thickness is not decreasing, you are safe because there's no corrosion. In case the thickness of the probe starts decreasing, this is a sign of corrosion, and you would say that you are not safe in this area. Whereas a straight line which just shows no loss of thickness and then no corrosion, you would say that you are safe, right? So comparing those two actually is a little contradiction, because these ones have actually been measured on the same coupon, on the same probe, on the same pipeline position. So the ER probe tells us here in this case that you are not safe in this area, but tells you that you're safe in this area. Whereas the potential measurement tells you that you're safe in this area and not so safe in this area. And here you're safe again. So how can that be explained? Well, you can go and have a look at the electrical fingerprints, which is the DC current density as well as the AC pipe to soil potential, AC current density, and the spread resistance. And what you will actually see here in the region that you by potential measurement have deemed to be safe, you do have quite a lot of DC current density. Negative, in my point of view, is cathodic. current density. You do have fluctuating AC potential up to 7.5 volt. So that gives you some kind of interference from AC. And you can see here that you also build up some AC currents, which are far below or far higher than the criteria from the AC corrosion standards. So in this case, the combination of actually too much cathodic protection and the AC is what gives you corrosion here. I'm not going to go into very big details, but you can see that one way of mitigating here is to get rid of the AC induced on the pipeline. Of course, that will give you a safe condition where you don't have any thickness loss on your ER probe. But you can also see that right in this period here, you still have high AC, but you don't have any corrosion. And what has happened here is simply that you have let go of the cathodic protection. You sort of loses the cathodic protection, and that actually gives you a more safe condition in relation to your AC corrosion scenario. So it's a little upside down here where we have help in diagnosing from the ER probe and from the electrical fingerprints. Tell me about representative period. If you didn't have the ER probe, you will have to analyze this electrical pattern. Can you tell me what is the representative period here? I'm not sure I can. The AC current density is ever fluctuating and ever increasing. So it's very difficult to say, well, in this period here, we should measure the AC current density and then use the AC corrosion standard for evaluating whether we are safe or not. That would not provide us with a good result. If you do have a look at this particular period between the two lines, you will also see that the AC current density here, despite having the same level of AC pipe to soil potential, the AC current density is heavily decreasing. And that's because of that effect of the DC current density on the spread resistance. So the spread resistance will be increasing, causing a decrease in AC current density caused by you have loosened your cathodic protection, and that will give you a very effective means of actually mitigating your AC current density simply by adjusting your cathodic protection. So this is what you can get out of detailed studies of these kind of figures. You have again the period here in between the two red lines where you can see that the spread resistance is ever increasing, and the DC current density here comes from 10 amp per square meter down to almost 0, meaning that you do not produce excess of alkalinity, and the spread resistance will increase, and therefore the AC current density will decrease as well. So instead of, or maybe in combination with, the establishment of AC mitigation wires, if I had a pipeline and if I was a pipeline operator, I would start looking at my polarization characteristics, make sure I don't cause the problems myself. Actually, we can prove with this technique that if you try to adjust your DC potential to a value of minus 900, something like that, millivolts, rather than minus 1200 or minus 1500, in that case, despite or regardless of the AC level, you will actually be safe regarding AC corrosion. And we have proved many times, we have around 18,000 sensors out there. We have proved many times that the operator is actually causing the AC corrosion himself. I can see that time is flying. I just want to illustrate the effect of DC current density one more time. If you polarize too much, your spread resistance will go from one healthy value to unhealthy low values creating a lot of AC current. You will create no corrosive condition, a corrosion conditions from a no corrosion condition, simply because you have turned the rectifier, hooked them up with too much current. In this case, actually, we go from 4.5 ohm per square meter, in spread resistance to as low as 0.15. This is one extreme example. You have 350 times reduction in AC current density just by reducing the CP level. And you could imagine how much grounding you should put in the soil in order to have the same effects of the grounding. So it's really a powerful tool to adjust your rectifiers to the correct value where you have a risk of AC corrosion. I think my time is flying very fast here.
That's Dr. Lars, not a problem at all. You can take your time. That's not a problem. We can always extend the talk for another half an hour. That's not a problem.
Okay, but I think I'm coming to the end.
Right, perfect.
This is just another example where you just you can see this is an example where we had the permission to play with the pipeline and where we had established the corrosion rate concept. And we also had the opportunity to play with cathodic protection. This is one level of cathodic protection, and this is a more severe level of cathodic protection, minus 1.6 versus minus 1.2. And you can see that we play with going from one condition to the other. We are also playing with disconnecting established AC grounds so that you can play with the AC voltage that is induced on the pipeline. You can see initially we do have almost no AC. We have a potential which is in this condition, and we have absolutely no corrosion. You can see that by the straight horizontal line here. And we start disconnecting. First of all, we do a more increase of the CP, and we show that as long as you have no AC, you don't create any corrosion. So then we start disconnecting the groundings successively, and we can see that the AC voltage pipe to soil starts increasing, and there is a daily variation. This is why, depending on the overhead power line load, this is why we can see those fluctuations here. But we start seeing that initially when we have a high level of AC and still moderate level of cathodic protection, we don't see any corrosion. But then we add more cathodic protection, just a little bit. We just add 300 millivolts in the on condition. And what happens? We can see that corrosion starts coming to the probe and therefore expected to the coating defects of the pipeline, if they're small enough. We can also see that the DC current is starting to increasingly, increase to more cathodic values. And if I had plotted the spread resistance, you would also be able to see that the spread resistance would decrease. And when you compare the corrosive situation here with a situation that you have created here in slot number 6, the only difference here is that in slot number 6, you still have a very high or quite high level of AC, but you have now changed your potential to more to less negative values, and you have gotten rid of your corrosion rate. So again, the corrosion rate concept can be used as simple means just by looking at the thickness of the probe, and it can be analyzed further if you would like to diagnose the cause of AC of corrosion. You can clearly see that this is an AC corrosion case caused by excessive CP in combination with induced AC. So I don't know if we have just 2 minutes to talk about DC interference.
Yes, of course, not a problem.
Okay. Say when it comes to DC interference, In my point of view, the NACE SP0169 gives some indications of how you can actually see if you have DC interference. And this is, for instance, by fluctuating potential like this. And then we ask, are we safe in this condition? It also in NACE SP0169, it tells you something about how to mitigate. But there's not really any firm criteria on how to evaluate if you're safe or not. So that's why I've turned to the ISO standard 21857, where there is a Q method. And I'm not going to go through that Q method, but it's a step-by-step procedure, which you may clearly see involves quite a lot of analysis. There are different steps to go through. One step, and the first step is select a reference potential, which is a value that you consider represents the protection potential you require for your pipeline, right? So it's a little awkward and a little backwards. You actually start by guessing on a potential that under these circumstances is meant to give you protection. But since you select it yourself, how do you select that potential? And how can you rely on that potential further on? I have been doing some analysis on this curve, actually by the help of the Consult website, which have a Excel sheet where you can use. And in this case, I have selected a reference value of minus 1110 millivolts as a reference potential. It calculates and goes through all the steps, and it gives you the diagnosis that this fails. So 1110 selected as a reference value gives you a non-compliant situation. Then I select here minus 1100, that's 10 millivolts more anodic, and then it passes. It doesn't really make sense to me that you can do it this way, just by guessing by a potential and what is actually that. What should you do with that potential, and how do you guess the right value? And in this case, of course, the corrosion rate concepts comes into play as well. These are measurements where you have we have made some interference study on a fluctuating system where trains come passing by. We measure the electrical fingerprints every 1 second, and throughout the day we can see that if you focus in 1 hour, you can see some electrical trains coming by and giving you some interference. So you can actually read the far plan of the train, also like this. Is this a safe or non-safe condition? You could go through this very, very complex step-by-step procedure, or you could simply look at the corrosion rate, and you can say, well, all of this doesn't really matter because we have a corrosion rate of 0 here, right? So as I'm coming to the end, I hope that I have made an illustration that CB compliance can be made quite simple also under interference condition. If you apply a corrosion rate sensor, it will simplify rather than complex the measurements, and it's very easy and straightforward to use. And with that, thank you very kindly for your attention. I know the floor will be open for questions, but please take my email address, and if some of you would like to discuss beyond what we can do today, give me an email. Also, if AMP India Chapter would be interested to have a further session where we go a little bit more in depth with corrosion mechanisms and how to measure, how to do, I would be very pleased to visit India sometime in the future, come back to India. So thank you very, very much for your attention.
Thank you so much, Dr. Lars. That was an interesting, pretty technically deep presentation, and I'm pretty sure the participants have also thoroughly enjoyed the same. Let me just unmute all the participants so that they would have an opportunity to talk to you. In the meantime, I'm just checking the chat box. We do have questions on the chat box. So the first question was from Mr. Srinivasa Rao. His question was, what is the range of PSP? That is the pipe to soil potential.
What the range is? If you mean the range where you are.
Do you want him to elaborate the question?
Yeah, well, maybe the question would be rephrased. Is there some kind of range of the cathodic protection potential that we should be within if we are safe also regarding to AC corrosion? And if that's the question, it's really something that depends from soil type to soil type, and also depends very much on the resistivity of the soil. But as a general rule of thumb, I would say make sure that you are not over excessive with cathodic protection. Minus 950 is to me a better value than minus 1200 millivolts, and that's in the on condition actually.
All right. Mr. Srinivasa Rao, if that has been answered, or if you want to elaborate the question, you can unmute and ask the question. I believe that question has been answered.
Okay.
All right, we'll go to the next question. Mr. Abdul Aziz has asked, is there any reference standard related to corrosion probe application on cathodic protection for corrosion monitoring? Do you want me to repeat the question, Lars?
No, there is. I don't have the number on top of my head. There is. I think it's. There is some guidelines on how to design coupons and how to apply them and use them in connection with cathodic protection measurements. And furthermore, we are currently within AMP developing a standard called field techniques for evaluation of AC, and that one gives you more elaborate guidance on how to design and apply and install and interpret results from probes in relation to pipeline as such. This is a standard that is developed right now. I hope it will be in the marketplace before the end of next year.
Mr. Abdul Aziz, do you want to elaborate your question? You can unmute and ask your question if in case you want to ask some details. In the meantime, we'll go to the next question, which is from Mr. Vincenzo. Sorry, which is the correct condition, the loose of CP for, not very sure how to read this, for that area means to be safe for AC corrosion, but how can we be sure that the cathodic protection is correctly functioning? Mr. Vincenzo, you can directly ask your question as well. You can unmute and ask a question.
I actually think I understand the question, and it's a little bit in the same family as the first one. How do we know that our cathodic protection system is actually working? I was so kind to illustrate a conflict when you measured the potential alone, and if you compared that with the corrosion rate. And I think that has been the intention of this whole talk, to actually trust a little bit less on potentials, a little bit more on currents, and a little bit more on corrosion rates, and actually using this system in combination and focusing on the corrosion rate. As long as you don't have any loss of thickness on your probe, the standards actually tell you that this is allowed as a documentation that your cathodic protection is under control. Remember again, as I mentioned in the first place, we need to focus on not so much potential and a little bit more on corrosion rates. The benchmark for cathodic protection is a corrosion rate which is less than 25 micron per year. So if you can document, and especially under these interference conditions, if you can document by a corrosion rate probe or by a corrosion rate test station that you are having corrosion rates less than 1 mil per year, 25 micron per year, in that case, you are actually safe. And then, of course, using the electrical fingerprints, you can also say, well, my potential is also in control. It's a simple supplement in complex situations, this corrosion rate test station. Yeah.
I hope that question has been answered, Vincenzo. All right, Mr. Parvatalu has a question. What is the limitation of the measurement using these probes? What is the limitation of the measurement using these probes?
Yeah. One would argue, and this is an argument I've heard so many times, that just like a coupon is not representing in proper way the pipeline. Why not? Because, well, the pipeline is a pipeline and a coupon is a coupon. And of course, that's correct. There might be some limitation is that you need a number of coupons along the pipeline in order to make this kind of evaluation. But on the other hand, if you really think hard, and I think we can maybe another time discuss that, if you have a variety of different areas or sizes of coupon defects on a pipeline, those defects will shield from each other. And you can actually show that the polarized potential of these the different coating defects are not the same. So I would argue that if you think that a coupon is not representative of a pipeline, I usually say back, well, in terms of evaluating cathodic protection, a simple measurement on the pipeline does not represent all the coating defects that you have on that pipeline. Whereas a coupon is a mimic of the worst case condition, and then you establish that worst case condition, and you measure according to that worst case condition, and that would be your strongest argument for using a coupon. But placing the coupon at the right place, also make the proper installation so that it's in contact with the soil and in the same kind of backfill, is the challenge with using coupons. Not only corrosion rate probes, but coupons in general.
Mr. Arun Kumar has a couple of questions. Mr. Arun Kumar, could you please unmute and switch on your video and ask your question directly? I would prefer that. In the meantime, the question is, what is the use of solar panel in test station? Yes, Mr. Arun Kumar, you want to speak? You can definitely speak. You can unmute and ask.
Good evening, everyone.
I think there's a lot of noise behind.
Very nice
we can't hear you very clearly, Mr. Kumar. Very less audible. Lars, can you hear Mr. Arun Kumar?
Oh, no, I cannot. But maybe in the meantime, let me explain the use of a solar power panel.
Yeah.
If you do have a remote monitoring unit or a data logger, of course, this one needs to be powered. And the simple use of a solar panel can be used as a very reliable and rugged way of powering up your device that has been embedded within the test station here. You can also use batteries, but again, you do need, if you don't want to visit your test station very often, you do need to have a continuous power supply to these data loggers or remote monitors. And today you can have batteries that last maybe, depending on the frequency of your measurements, that last for 3 to 5 years, and also solar power panels that we have panels that have been functioning well without any problems for 10 years in such a test post. So the use of solar panels is a very common way, or a good way, at least robust way, to provide power to the data, to the electronics that you embed in the test post. If you have problems with vandalism, of course, this type of test station where you signal that you have some instrumentation inside may not be the best. But that's where we have the underground bullet, so that you can hide completely what you have. And of course, that has to be combined with a battery. I don't know if that answers some of your questions.
Lars, I hope Mr. Arun Kumar is able to get a good connection, because there seems to be a lot of disturbance behind.
Yeah.
I think in the meantime, we can just go over to Vincenzo. Mr. Arun Kumar, I would request you to please check in the internet connection and then rejoin in, because I think your next question is related to a graph. So we'll get into that after we answer off with Mr. Vincenzo. Mr. Vincenzo, I think you still have a question. Could you please
Yes,
unmute and answer?
is it possible to make a question live, or
Yeah,
if it's
please, I can hear you.
okay, thank you very much. First of all, thank you for your presentation, and thank you to AMPP India Chapter for this opportunity. Just a little question related to my previous question regarding the cathodic protection level. Okay, I understand that we have to reduce as much as possible the pipe polarization, but I suppose that what you've shown before is also related to the soil resistance. So I don't know if you have experience in different soil types. For example, I mean, sandy soil, if there is a great difference between a soil full of clay. So in a case which we have too much water, and in a case in which we have too much oxygen, like sandy soil. And also the spread resistance, if the spread resistance is related more to, as I understand, to the coding resistance, not only to the soil resistance, resistivity, sorry. If okay.
Yeah. First question first. Of course, there is difference in the different soil types, and there are also effects of the different resistivities of those soils. But my point is that every time I have seen problem with AC corrosion, it is actually caused by the operator themselves, because they have taken control of the environment. And again, it's related to this equation here, where you when you model things, you model the AC voltage, and you think by this equation, if you measure the soil resistivity, and you know about the coating defect, geometry, and size, then you can calculate the AC current density. And I've spent my whole career warning a little bit about that simplification, because it's not the soil resistivity which is the primary factor. It's the DC current density, and whether that DC current density starts to reduce the spread resistance, because then you have your autocatalytic circuit where AC corrosion is going faster and faster and faster. So you have to get the other way back out of that circuit. And that is, you cannot change the induced AC other than grounding the pipeline. You cannot change the coating defect geometry, but you can certainly change the cathodic protection. So turn down a little bit your cathodic protection system, and then this circuit would start, instead of running in this direction, let it go in the more healthy direction backwards and recreate a condition where you do not affect the spread resistance. This one will carry on, and I illustrated that in the very extreme cases, we had a reduction of 350 times, meaning that if you, for instance, can model that your AC is at 15 volts without grounding and 3 volts with grounding, then you have attenuated that AC voltage by a factor of 5. But if you at the same time, in order to make very sure that you don't have any corrosion, turn up your cathodic protection and goes to a situation where your spread resistance decreases by a factor of 25, then your combined action have actually increased the probability of having AC corrosion by a factor of 5, to put it simple. So you can make that kind of modification of the soil in almost any kind of soil. But if you have magnesium or calcium in the soil, instead of sort of creating a lower spread resistance, you can also have an increased spread resistance, and thereby the whole situation comes into balance again. So yes, the environment has a very high effect on whether you get AC corrosion or not. But it's very difficult to tell in advance which kind of environment do not create AC corrosion, in my experience.
Okay, thank you. Mitigation for you are also related to the use of earthing electrodes through polarization cells or overvoltage diverters,
Yeah.
or mitigation means just reducing the pipe polarization?
I think for safety reason, you need to look at a potential that should not go beyond 15 volts of AC. So you do need to consider a grounding strategy. But all the curves that I actually showed here was at say this is 7.5 volts of AC maximum, causing a whole lot of AC corrosion, and there's no need for grounding when it comes to safety reasons here.
Okay, thank you very much.
And I'm just saying, please, before you start doing some costly AC mitigation here, try to make use of the polarization, the cathodic protection concept as a first measure, and then consider AC mitigation afterwards. That would give you the most cost-effective solution.
I hope that question has been answered, Mr. Vincenzo.
Yes, thank you very much. Sorry for my questions.
Thank you. Thank you. Back to Mr. Arun Kumar. If you can unmute and ask your question, because his question is related to a graph. So he says, I'm a bit confused about the graph in which you're comparing the corrosion rate of probe and the PSP values. So can we take this question, Lars?
Can I have the question, please?
He says, I'm a bit confused about the graph in which you're comparing the corrosion rate of probe and the PSP values.
Yeah, and that might be this one, where according to the corrosion rate concept, I'm not safe because I can see that I have corrosion created here. And the PSP, pipe to soil potential, tells you actually that you are safe. And one of the points here with using the corrosion rate testation technique is that if you, in this case, had only pipe to soil measurements, you would just lean back and say, I have no problem. But actually, you do have a problem. And that problem is the combination of too high cathodic protection, which, if there was no AC, would be fine. But since you have an AC element in this particular situation, the combination of an otherwise safe potential, which is too excessive when it's combined with AC, and the combination of that AC will give you a non-safe condition. And this is why I'm trying to compare how easy it is to look at the signal from an ER probe. It's equally simple as to look at the potential, and it gives you more reliable results when you have AC or interference conditions, because in that case you would fail, you would not interpret the pipe to soil potential correctly as a safe condition, simply because you have AC on your pipeline. So that's a little tricky, I know about that. AC puts everything upside down. And you need to understand that in order to mitigate AC corrosion in a proper way. Did that answer the question?
Mr. Arun Kumar, I hope that question has been answered. If you can unmute and answer that, that will be good. In the meantime, we go to the next question, Lars. So Mr. Kula Sekar has been asking, what is the life of the ER probes and the reliability of the data in the long term?
Yeah, good questions. The lifetime of an ER probe is in principle infinite, considering the case that you do not have any corrosion. So if you do not corrode on your ER probe, it will keep on working as long as it's not, cut down or stolen or vandalized in any way. And therefore it can be very long time reliable. If you do have a corrosion case that goes very, very rapidly, the probe can be worn out. But I think that if you do have a proper understanding of what you need to do when you see a probe corroding, I mean, if you do have a proper understanding on how to mitigate this, you can sort of rescue the probe and thereby rescue your pipeline by doing actions in due time. If you lose an ER probe, well, you need to bury another one. And that's the price that you have paid for becoming aware of that problem that you have. But in most cases, and the operators of our ER probes have come to an understanding that if the ER probe is telling you a warning, I have corrosion, they need to go through the electrical fingerprints to find out why and make corrections so that the probe is no longer corroding, and therefore the pipeline is no longer corroding or in risk of corrosion.
Okay.
Yeah.
So we can go to the next question. Mr. Parvatalu has probably two questions. I'm going to combine them. The same coupon can be used as a probe also for periodical monitoring. I mean, provision for in situ corrosion measurements can be made.
Yes, the probe can be used in many ways. The most informative is when you have a continuous monitoring or data logging of the probe. And if you see the data every day by remote monitoring, you will have instant access to the data. You can also use it in such a way that you have installed the probe and you connect it directly to the pipeline without any data logger. And then maybe every 3 months or every 6 months or every 12 months, you come back to see what is my thickness of the probe now. And in case of any change in the thickness of the probe, you do have some kind of flag, a warning that something is going on. In that case, you might consider establishing a data logging so that you can start diagnosing what is actually the cause of this reduction. But clearly, an ER probe can be used in combination with data logging, remote monitoring, or spot-wise measurements. And also an ER probe can be used as a coupon, exactly as a normal coupon. You can disconnect it and make IR free and off potentials. You can make DC currents and AC currents on that ER probe, so that in addition to what you can measure on a coupon, an ER probe also measures corrosion rate.
And we have the last question from Mervyn Joseph. What is the ideal distance the ER probe should be placed away from the structure?
Let me see if I have some pictures here of the different probes. Usually we recommend that the probes should be as close as possible to the pipe surface. And at least it should be in the same backfill and therefore in the same environment as a chemical environment and physical environment, the same soil, the same dirt as the probe itself. Some operators, they prefer to have such a flush sleeve. So if you make an excavation of your probe, you can actually put this probe directly on your pipe and make it sort of flush with the pipe, so that to the best possible degree you mimic what is happening on the pipe itself. But it should definitely get to the same depth of the pipe and definitely get into the same environment and backfill of the pipe as the pipe. And it should be, one should make sure not to use any water when you are installing the probe, because external water would change the chemical environment. So don't do that. You should also make sure that the probe and the probe surface is in very good contact with the soil. And you can check that by measuring the initial spread resistance to see that there is actually no voids between the probe surface and the soil, and therefore that there is a good contact between the soil and the probe.
I hope that question has been answered, Mervyn. So that was the last question, Lars.
Amarjit,
Yes, sir.
KB Singh here. I have a few questions. Lars, excellent presentation.
Thank you.
AC coupons which are being installed, and the entire basis of AC mitigation is based on the AC current density through 1 centimeter square holiday, which is made in the coupon. Now, how do we maintain these coupons? Because obviously there will be pitting on these surfaces of the coupon. What's your experience, number one? Number two, when should we replace them?
If you buy an AC coupon, that means a coupon that for some reasons have been designed to measure the AC current density, and usually this is a circular 1 square centimeter coupon. I don't think you have any chance of maintaining a coupon like that. When it's buried, it's buried. And but of course you should measure on that coupon. And you say inevitably that there can be some pitting generated on that coupon. Say if you operate your system as I have tried to illustrate, if you operate it in a good way, there shouldn't be any pitting on that coupon and no corrosion on that coupon. And if you use a coupon, if you use an ER probe as a coupon, then you have a quality, you have a means of evaluating whether the coupon is valid or not. Because if you don't measure any thickness changes on the coupon, then there's no corrosion on the coupon, and the coupon is good to go. I mean, you do have a validation of also the use of the coupon for current density measurements. If the ER probe is intact, haven't lost any thickness, or you know that it still has some thickness left, in that case you can use it as a coupon. because
so your recommendation is not to use a normal AC coupon, because I've seen pitting on some of the coupons in India. So your recommendation is to use ER probe, which will back up as a coupon, AC coupon.
yes, that is my clear. If you're looking for AC corrosion, I just find so many advantages of using an ER probe as a coupon, because you are able to validate the coupon quality, you can say, and you are also capable of measuring the corrosion rate on that coupon, on that ER probe. So
Thanks.
I really see good benefits
Yeah.
of using. And again, it gives you a way to validate if your control measures are working as you intend them to work.
Good. My second question is, in case of a fault or AC fault, the pipe may be suffering very close to the transformer and there is a phase to ground fault. We have seen coatings getting damaged. We've also seen steel getting melted due to a high fault current. Do we have any development of probes to check that if the pipe has been subjected to any fault current?
I have to say the short answer is no.
Any development on the way? Because in India we have this problem. We are seeing a lot of failures due to AC fault currents.
Yeah. And these are failures that actually affects the pipeline integrity?
Yes. Because the fault currents could be almost 8,000-10,000 amperes, and if the pipe is very close, we have seen that the current enters into the pipe and has caused pipe integrity problems.
Yeah, and usually the fault has a certain duration of
It's only about 200 milliseconds, but that's sufficient enough to cause the damage.
Really? Okay. And not only to the coating.
Yeah, no, the coating over the pipe. I'll share some photographs with you. So if you can start working on that, because that's a huge problem today in countries like India, where the distribution transformers earthing is extremely close to the pipeline.
Yeah.
It may not be a problem in the western part of the world, but in countries like India, Bangladesh, where the right of way is restricted and we are sharing common corridors with these 11 kV, 33 kV networks.
Yes, sir. Yeah. I think it's a slightly different approach, and indeed a different analysis that we need to go through. These kind of fault currents have nothing to do with cathodic protection at all.
Yeah.
So this whole concept is not suited for these fault currents, I have to say. But it's an interesting approach.
Yeah.
And usually when you're making standards, I think maybe it's for convenience among the standardization people.
Yeah.
They say that only steady state can cause AC corrosion. But I do acknowledge, sir, that these kind of fault conditions might also influence the integrity, and another approach is needed there.
Fine, that was mine. So much time through, you can take it forward.
Yeah.
Thank you very much, sir. And with that, anybody else has any other questions can quickly unmute and ask the question. Else we should close the technical talk with a vote of thanks. Anybody has a question can unmute and ask at this point. If not,
I have one question.
Menu speaking.
I'm
Mr.
Kulsekar.
Yes. If you can show your video as well, it will help.
Yes, ma'am.
Yeah.
Ma'am, its video tab is not working. I will ask my question.
Right. It's all right. It's all right. Yes.
Sir, how much safe your this corrosion coupon for the particularly LG faults which is coming from the pipeline surges? So this coupon will be safe from the electrical surges coming from pipeline?
If the coupon will be protected from surges, is that what you're asking?
Yes, sir.
Yeah, and yes, to a certain degree, you cannot protect against any kind of electrical surge. It's about where does that surge come from? Is it a lightning surge or whatever? But there is in at least in our data loggers, there is a heavy surge protection, and and that has been developed because in the beginning of our career as providers of data loggers, we did realize that data loggers, they are exposed to those surges, and we have developed in our case a very heavy surge protection. I do not have them defined right out of my head, but you're welcome to come forward and ask me on an email for our specifications. And that surge protection usually, and in most cases, and this is the experience of our many users, prevents any damages to our probes.
Including electronic boards, sir?
Yes, sir.
Okay. Thank you, sir.
Yeah.
Thank you, Mr. Kulasekar. And with that, we have come to the end of the technical talk. With us, we have our Secretary Madam from AMPP India Chapter, Nivedita Ma'am. Nivedita Ma'am, if you can hear me, could you kindly unmute? I think there was some internet issue at her end. That was the problem. I wasn't able to communicate with her. If in case you can hear me, ma'am, you can unmute and switch on your video. I believe ma'am is having some issues. Yes, ma'am. Are you able to use the mic and the video, Nivedita madam? I believe there is some kind of IT issue, Lars. I'm sorry about that. I would request KB sir, could you please extend a vote of thanks to Dr. Lars, who has joined us for today's eminent talk?
Yeah, sure.
Thank you, sir.
So, on behalf of AMP India, Dr. Lars, I sincerely thank you for finding time for this excellent technical talk. All of us in India are aware that AC interference is becoming a real threat to our pipelines. 20 years back, when we were also young, we had not heard anything about AC interference. We were only worrying about polarization on the pipelines. But now in the last 5 or 7 years, we have pipelines sharing corridors with transmission lines up to 765 kV. So I've seen pipelines where almost kilometers together, the right of way we are sharing with 132 kV, 220 kV, 400 kV, 765 kV. We are seeing induced voltages going up to 40 volt, 50 volt, 60 volt. We can even light a bulb. There is so much of induction on these lines. And as you have rightly said, mitigation is becoming a big cost. It is not easy to put everywhere zinc grounding cells or zinc grounding ribbon anodes coupled with DC decouplers. So it is good that you have enlightened all of us that by using DC, we can control the spread resistance. I'm sure we will take more lectures of yours. We need the operating engineers to understand exactly how spread resistance works. In half an hour or 1 hour talk, I don't think so you will be able to enlighten them, but at least this is a beginning. We would request, depending on your convenience, a visit to India where we can facilitate and have a better conference where you can probably take a 2, 3, 4 hours of technical lecture to make the people, including me and my team, to understand how the spread resistance is controlled by DC current, which would eventually reduce AC corrosion. So again, I thank you for your time, and we look forward to your visit to India in near future, which we will send you an invitation for a technical talk, or I would say a technical lecture extending over 2 or 3 hours. Thank you very much.
Thank you. I'm I'm very.
Thank you very much, sir.
Yeah.
Yes, Lars.
Thank you very much, sir, and thank you, Amarjit, also for helping me in understanding how to do all of this stuff. It would be my utmost pleasure to come visit India again. It's been a few years since I was there last time. And if we can make a session through AMP India section, and if you would like me to come to participate in a seminar, that would be my utmost pleasure. And today's little talk, I do hope that it has been illustrating just a little bit of my points. And I'm not saying this is a solution to all problems in the world, but I have a feeling that it's a contribution to at least a better understanding of both how to monitor and how to mitigate AC and how to avoid AC corrosion on the pipeline in the future. So I hope it's been beneficial for those of you who so kindly attended this technical talk. It's been my great pleasure, and I thank you all for taking your time so late Friday afternoon, evening. I'm not sure you're going on weekend in India, or do you have work on Saturday as well? At least I hope for you that you can go back to your homes now and have a nice Friday evening.
Thank you, Lars.
Thank you so much, Lars. Just a quick thing for the participants.
Amarjit, just a minute. And I would also thank all the participants for attending this technical talk. If you have any doubts, if you have any questions further, please send mail to Amarjit or to Rishi. We will get back to Mr. Lars and request him to respond to your questions. This is an important topic, number one. Number two, we would continue to do such technical talks. We would appreciate if you can send us your thoughts, your ideas on which subjects do you want such more technical talks to happen. We are putting up an itinerary for the next 8-10 months, so I would sincerely appreciate if you could send a mail across to Amarjit and Rishi, who are the officers of AMP India Chapter, so that we can plan for future virtual talks like this. And lastly, I'll thank Amarjit and Rishi. It takes a lot of planning to organize such virtual thanks. So Amarjit and Rishi, many thanks for organizing this. Thank you very much. That's from my side.
Thank you very much, sir. Thank you very much, dear participants. I request all of you, since I requested you for your video to be switched on, just switch on your smile as well. Just a quick smile. All right, I've taken one snapshot. If I have missed someone, not very sure. This video, the screen that was switched on, just give me one more screenshot, one more smile, please. I think someone is adjusting the mic. Okay, yeah. All right, great. I will be posting this on LinkedIn. If you are following us on social media platforms like Instagram, Facebook, and LinkedIn, you will find many more things to be posted online, and you'll get updates about technical talks and courses that we are organizing. Please do not forget to subscribe to our social media platforms and to check out our websites as well. So we have a couple of upcoming courses as well. So Rishi, if you want to talk about some courses, you can definitely update the participants. In the meantime, we shall be organizing a workshop on CP design, and you will be getting to know about the details pretty soon on social media. The first CP design workshop will be held on 3rd and 4th February. And that's going to be in Delhi. That is in live mode. So book your seats if you're interested for the same. We shall be posting the details soon on the social media platforms. Thank you very much, everyone, once again. Thank you, Rishi. Thank you, KB sir. And a very, very hearty namaste. And thank you to Dr. Lars, who has taken out his really valuable time. A very happy Merry Christmas and a happy, happy New Year to you and your team, Lars. KB sir, Dr. Lars had his Christmas lunch along with the team today, which he'll be joining soon. So please do extend our wishes as well from India to your entire team. Thank you so much for your time. We really look forward to all of you participating again in another valuable technical talk. Thank you once again. See you next year in January with another good technical talk. Thank you so much for your time. Namaste.
Thank you. Thank you.